Hi, this is Team 10, and we're going over adder subtractors using XOR gates.
The adder-subtractor unit adds or subtracts based on the value of Cn, and it makes use of 2's complement for the subtraction. The design for this adder-subtractor unit consists of full adders and exclusive OR gates. To be more specific, there are 4 full adder units connected together to form a 4-bit ripple carry adder. This is what allows us to pass in 2 4-bit inputs. The subtraction is done using the exclusive OR gates, which is how 2's complement is implemented. So as you can see, there's 1, 2, 3, 4 full adders here, all connected together. And there is actually an additional component of the adder subtractor unit, which is another exclusive OR gate drawn out here. So what this does is it takes in the last 2 Couts, which is the one highlighted in red and then the one right before. And what that tells us is whether or not there's an overflow for the output. So what that says is if there's an overflow, there are not enough bits to represent the number that you want to show for that A and B creates, either by subtraction or addition, which means that there is going to be 5 bits or more to accurately represent the number that you want to show.
Okay, so the addition component of the adder subtractor can be straightforwardly designed, having a control input of sub, that is the subtraction unit, and it can be abbreviated to SUB, that's sub. And if this component is 0, so if sub is equal to 0, the adder subtractor component performs the addition operation. So as you can see that this subtraction variable is attached to the XOR gate with the input of B here, 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 and here. And going through the XOR truth table, and in place of A, I would say sub, and B is as it is, and F is what is resulted out of the XOR gates. So when sub is equal to 0, considering B is 0, the output is 0. And when B is 1, the output is 1. So this tells that there is no change, which means that for the addition process, when sub is 0, the input of B's are passed through as it is, and the adder subtractor performs the addition operation. Now, for example, suppose A is 0011, that is equal to 3, and B is 0100, which is 4. Now looking at the decimal representation, the sum of these two should equal to 7. Now going through the binary operation 0011 0100, we know that 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. And now the decimal representation of this output is equal to 7. So it does verify the addition process. And yeah, that's it.
Right, so now let's see how we can do subtraction using this circuit. We know we can write subtraction A minus B as A plus B naught plus 1. And when we do subtraction, we have to say that our sub bit is equal to 1. That means that we have 1 going into the XOR gate with all of our B values over here. Now, when we have a 1 XORed with something, the output of this XOR gate is simply going to be the inverse of whatever was in. And we can see that from the truth table over here. If we have 1 and 0, the output's 1, 1 and 1, the output is 0. And A is simply fed in as is into the full adder. And we have our CN, or our sub, is equal to 1, which goes into our CN. So as you can see that our full adder is just doing A plus B naught plus 1. Alright, now let's work an example. Let's say that our A is equal to 0, 1, 0, 1, and B is equal to 0, 0, 1, 0, which is 5 minus 2, which should give us a 3. So we have a 0, 1, 0, 1 going straight into the full adder, and obviously we have to have a sub equal to 1, and we have our B's equal to 0, 0, 1, 0. So the output of the XOR gate is now going to be what? We're putting in, starting from right to left, we have a 0 and a 1, so it's going to be 1. We have a 1 and a 1, it's going to be 0. 0 and 1 is going to be 1, and 0 and 1 is going to be 1. And we have a CN into the first full adder equal to 1. So 1 plus 1 plus 1 is equal to 1 with a carry out of 1. So our S0 is equal to 1 with a carry out of 1. Now what's our second full adder doing? It's doing 0 plus 0 plus 1, which is equal to 1 with a carry out of 0. Our third full adder is doing 1 plus 1 plus 0, which is equal to 0 with the carry out of 1. And our last full adder is doing 0 plus 1 plus 1, which is equal to 0 with a carry out of 1. And we can see that our sum is 0, 0, 1, 1, which is equal to 3, which is indeed correct. And our last carry in and our carry out of the circuit are the same, which means no overflow. So we're all good.
The 4-bit adder subtractor makes use of 2's complement to modify the B input depending on the CN value. This way, both addition and subtraction logic can be done using only the full adder unit. Thanks for watching our video.